So how do we handle the color dependency of the extinction coefficient? The easiest way to understand that procedure is still expand your color dependence term. Okay? So still expand your the extinction coefficient into the multiple series constant first order the constant and first order and second order term, and then parameterize in such a way that actually zeroth order term is simply a constant. It simply there is no the dependency other than the air mass. Second term is the most the dominant next term is that because of the previous the understanding of this Forbes effect, so that is actually that the second order term is dependent on the spectral shape of your the source, meaning that actually imagine this the blue star seen through the shortest path length, which is actually right above your head, zenith around the zenith angle of 0, versus that actually blue star seen through the near to the horizon. You see that actually the light are actually all scattered off through the Rayleigh scatterings, whatnot. That actually your color of the source near to the horizon at high air mass is drastically different from the case of the high altitude. So that is actually the spectral or color dependency of your. But compared to that, actually, the blue star case, red star is already that actually is a red. So that actually whether that actually you are observing right above your head or that close to the horizon, that actually effect of the spectral shape modification or red star is not that drastic compared to the blue object. So that is actually one way of understanding Forbes effect. Then the next higher the the stronger effect is such as the changing the atmospheric composition in terms of at the level of atmosphere, the atomic level, such as the water vapor content is changing. You know that actually water vapor is causing certain extinction as a function of wavelengths, meaning that actually if your passband is including water vapor sensitive layer, then then the changing water vapor level, so they're actually drier versus the more the wet, moist air, that can actually that not showing the overall the extinction variation, such as the zeroth order and the first order term, but that actually that can add the additional the second order term, the effect. But usually that actually this the second order terms such as the water vapor or slight variation of temperature or pressure, that refractive index is changing, and also that actually as a function of the altitude, that actually that the refractive index is also dependent on the altitude, so called the differential refractive index changing, so differential atmospheric refraction. So these are actually all in the higher order secondary term. And usually this contribute to something like the 1,000th of magnitude difference level, that the first order term, like the color dependent effect, this is usually contributing something like the 100th of the magnitude level effect. And at the simple that actually that at the air mass zeroth order, the effect is actually working at the level of magnitude. So usually we ignore the higher order term other than the spectral or the color dependent. The extinction coefficient can be simply expressed as the constant plus color dependent term. So color dependent extinction coefficient, and then the constant the extinction. Then your observation instrumental magnitude obtained through your the atmosphere A, and the difference between that actually atmosphere affected the magnitude versus atmosphere free magnitude is simply that the the zeroth order, the extinction coefficient versus that actually first order term multiplied by the color of your object. The whole thing is actually dependent on the patterns of the. So the key issue is actually then how do you actually obtain this case of 0 and case of 1. So color of the object of your target can be obtained in some way, and then as you